Good morning, Prof. I'm sorry, but we are not able to hear you. Can you unmute the microphone?
Okay, now it's better. I hope so.
Yeah, we can hear you now.
Okay, thank you. Sorry. I assumed it was okay because, strange enough, I didn't get any warning by the micro. Okay. Yeah, sorry? It's okay, perfect. Can you please close the micro? You are remotely connected, people remotely connected, if you can close the micro, or otherwise I can close it, just 1 second. Okay, still I hear some noise, but I hope it's not a problem for you. Okay, so as I said, I was discussing on Monday when I closed the last lecture, I was discussing how to estimate the difference in elevation between the different spillways. So what I said is that when I closed, I said that we need a relationship relating the environmental flow to the water depth that is needed over the spillway to deliver downstream the environmental flow. I want to introduce today this relationship which gives the flow over a spillway. It's a relationship that comes from fluid mechanics. Before I move forward with the relationship, let me just discuss a little bit general criteria for deciding the elevation of a barrage. So I'm just now referring to the overall problem of the elevation of a barrage. It's clear that when we build a barrage, we can build a low barrage or a high barrage. And intuitively, you understand that the higher the barrage and the higher the accumulation of water volume upstream. So, I mean, if the barrage is more elevated, then I can rely on a larger volume of water that is stored upstream, which is an advantage because in case I have excess of demands, I have a reserve to use. On the other hand, you understand that if the barrage is too high, there might be problems. The first problem is that you should avoid, as you see in the first bullet item here, you should avoid that the storage, the upstream storage exceeds 1 million of cubic meters. And we should, the second bullet point, we should avoid to adopt heights that are higher than 15 meters, because if we exceed one of these two limits, then we go under the jurisdiction and the regulations of the National Service for Dams. Other recommendations: the upstream water profile should not induce an increase of the risk of flooding. Of course, when you build a barrage, you cause an elevation of the water depth upstream. We need to make sure that this increased water depth doesn't imply an increased risk of flooding. Furthermore, the barrage should not compromise the stability of the riverbed and the hill slopes. What is the implication? The implication is that if you are concerned by the stability of the hill slope, an higher barrage may be appropriate, because on the one hand it stabilizes the hill slopes, because the accumulation of gravel and loose material upstream, the barrage, contributes to the stabilization of the hill slopes. On the other hand, if you have an infiltration of water into the foot of the hill slopes, this may undermine the stability. So a proper geological assessment is needed in order to check what is the implication of building the barrage in terms of stability of the hill slopes and the riverbed. And finally, you have to evaluate the sediment transport associated to the river, because sediment transport causes siltation upstream the barrage, which means that the storage volume is reduced, and therefore our capability to benefit from a reserve of water is undermined. Okay, now let's go back to our problem, which is then, let me go to the blackboard and let me change the camera. Okay, very good. And let me share the screen for a moment, because we don't need to look at the web pages just now. So let's try to make a sketch, a frontal view from downstream of the barrage. So basically, you have the main spillway here, main spillway, which is conceived to evacuate the flood flows, as I said. And then you have the wings of the barrage. These parts are called wings. These are the parts that are more elevated with respect to the main spillway for the purpose of keeping the flow concentrated in the center of the riverbed. And this is the side wall. Side wall. These are the wings. Okay, now, at a lower elevation with respect to the main spillway, I have the withdrawal spillway, the diversion spillway. So this one is diversion spillway. Be careful, in the scheme that I used to introduce the river barrage to you, the diversion spillway is located on the side walls. Therefore, its extension is along the longitudinal direction. In this case, I am depicting here, I am sketching it here in the transversal direction just for the sake of clarity, okay? It may be in the transversal direction. It's not, we are not obliged to put the diversion spillway on the sides of the barrage. I said that it is recommended because in this way you have a limited likelihood, the probability of intercepting floating material. If you displace the diversion spillway frontally, transversally with respect to the river flow, of course you may get some floating material. If you displace the spillway, the diversion spillway on the sides, this probability is lower. But for the sake of clarity, let me show it here. And let me call with the symbol delta H1 the difference in elevation between the main spillway and the diversion spillway. And then at a lower elevation, we have the environmental flow spillway, and then we have the wing again. Wing. And this is the environmental flow spillway. Good. Okay, and let me call with the symbol delta H2 the difference in elevation between the diversion spillway and the environmental flow spillway. Let me also put a separation here, okay, just to keep them separated. Okay, perfect. Now, my question is, after considering the recommendation that we discussed just 5 minutes ago, how can I compute these differences in elevation, delta H1, delta H2? First, remember that environmental flow, let me call it EF, has priority. So this is why it's the lower. The environmental flow spillway is the lower. Okay, and what I said is we have to make sure that we don't divert any water until we have the environmental flow spillway downstream. We have the environmental flow downstream. The environmental flow, let me call it QDMV. DMV because in Italian it is called the flusso minimo vitale. Actually, it's a term that it's which means minimum vital flow. It's not a good terminology because it looks like the fishes are just, you know, and it shouldn't be a minimum vital flow. So even in Italy now we call it ecologic flow or environmental flow. So in Italian it's the flusso ambientale or the flusso ecologico, which is more used. Okay, so what is the moral of the story? When I have some flow arriving from upstream, this flow goes down through the environmental flow spillway. Okay? And I have to make sure that until I reach the value of QDMV here, through the environmental flow spillway, I'm not diverting any water. So delta H2 should be designed in a way that when I reach the threshold of the diversion spillway with the water level upstream, through the environmental flow spillway, I have the passing of the environmental flow. And therefore, I said I need a relationship that relates QDMV to delta H2. And this relationship is given in this form: QDMV is equal to a flow coefficient, me, let's call it me, and then I have the width. I don't remember how I called it in my slides, just 1 second. I need to check. It's LC, okay, LC. The width, LC, of the spillway, so me, LC, and then I put here delta H2 square 2G delta H2. This is the relationship that comes from fluid mechanics. Please learn by memory, okay? It can be easily proved, but we don't prove it because it's, as I said, it's a relationship that comes from fluid mechanics. This can be rewritten in a simplified way in this form: Q DMV is equal to me LC delta H2 to the power of 1/2 and 2G to the power of 1/2. This is the relationship that you see here on my slides. Let me share it for a moment. This is the relationship that you see here. Now, what is our interest? Our interest, what we know is QDMV. How can we know it? The QDMV usually is given by the legislation. it's technical guidelines or laws in force. So we know QDMV. What we have to determine here is delta H2, which can be easily derived from this relationship. If we, let me take the eraser. The explicit representation for delta H2, I'm writing it here. Delta H2 is equal to QDMV divided by me LC square root of 2g to the power of 2/3, yes. This is the representation I'm interested in. This is the relationship I'm interested in. So you may say, how can I determine LC? LC, usually there are technical guidelines, legislations that tell you the minimum value for LC. The minimum value should allow fishes that climb up to pass by, because usually downstream the environmental flow spillway, we locate the fish ramp in order to give the fishes the opportunity to climb up, in order to avoid discontinuity in the ecological environment of the river. And therefore, what is the minimum width for the environmental flow spillway? There are, for instance, in this region, there was a legislation some time ago that suggested a minimum of 40 centimeters. You know, the larger the environmental flow spillway, and the better is in terms of making sure that we have downstream a good environmental flow. If we reduce the width too much, it is a bit concerning for two reasons. One reason is purely, let's say, not technical, and is the fact that the environmental flow spillway can get stuck by floating material. So floating material can, if the environmental flow spillway is too shrinked, then if you have floating material, it can create obstructions. So this is a non-technical reason. But there is also a technical reason for suggesting that the environmental flow spillway should be kept as large as possible. The reason is that once that you have the environmental flow that is ensured downstream, you can start diverting water. And look, with this relationship, by computing delta H2 in this way, I want to draw your attention once again. I am making sure that I'm not diverting any water, because the water level doesn't reach the diversion spillway. So I am making sure that I'm not diverting any water until I ensure downstream the environmental flow. So the whole rationale here is to make sure through this computation that I'm not diverting any water. I am locating the diversion spillway at an elevation such that I'm not diverting any water until there is the environmental flow passing through the environmental flow spillway. This is the whole rationale. Then, if you have an increase of water level, again, upstream, because you have excess water arriving, then it means that you get to a higher water level and you start withdrawing water, withdrawal. Perfect. While you start withdrawing water, the water level increases also over the environmental flow spillway. And therefore, it turns out that downstream you have more than the environmental flow because the water level is increasing. And according to this relationship here, if you see, if you increase the water level, you get an elevation that is higher than delta H2. You have a flow downstream that is greater than the environmental flow, which is fine. I mean, the important thing is that it's not less. If it is more than that, it's fine. And the larger LC, the larger the width of the environmental flow spillway, the larger the excess of flow that you are granting downstream through the environmental flow spillway. This is the technical reason why the administration usually tries to push us to adopt a width of the environmental flow spillway that is larger, that is large. Because in this way, they make sure that when we start diverting water, there is also an increase of the environmental flow downstream. Okay? And this is the reason why they don't want a gate here. They don't want gates to avoid obstructions, because of course, if you put a gate, then the floating material can generate obstructions. But also they don't want the gate because the gate is a way to regulate the environmental flow. Once I reached it, I can close partially the gate and I can limit the environmental flow downstream. So they don't want the gate, and they try to suggest that the width is large enough. I hope that you got the rationale of designing delta H2, and you got the rationale behind the suggestion of increasing the width of the environmental flow spillway, not to take a spillway that is too shrinked, too thin. I hope it's clear. Now, the water level raises, so I have two effects. One, I start withdrawing water, which is fine. The second one is that my environmental flow is increasing. Good. At a certain point, I get to a water level where the withdrawal is equivalent to QP. So I am withdrawing all the water, all the design flow. I don't want to withdraw any more water because if I exceed the design flow, I cannot bring water downstream. Okay? So when I have QP, which is my design flow, through the diversion spillway, then I can start evacuating the excess water through the main spillway. And this is the condition that I impose to estimate delta H1. And how this condition is imposed? Very simply, by computing with the same relationship the flow through the diversion spillway. But of course, now I have to use as known flow, QP, and as unknown difference in elevation, delta H1. What I obtain is this. You see, it is the same relationship with QP instead of QDMB and delta H1 instead of delta H2. So with this simple relationship, I can compute the difference in elevation between the environmental flow spillway and the diversion spillway, and then later the difference in elevation between the diversion spillway and the main spillway. As I said, I really don't aim to withdraw more water than QP. So this is why usually we put gates on the diversion spillway in order to be able to regulate the flow. And in case we get excess water, there is a weir in the sand trap. You may remember that. There is a weir that allows us to bring back the excess water that I took through the diversion spillway, bring back it to the river. So this is the moral of the story. And let me just go back here to the sketch. What you see on this sketch is that first the diversion spillway is in the longitudinal direction. We already discussed that, which is fine. And then I have the top spillway here in the sand trap to deliver back excess water. The top spillway may be located in the sand trap or better in the gravel trap. It depends. It depends on the configuration of your site, and of course you have some flexibility. The important thing is that you put gates here, and the reason also for putting gates is not only not to exceed the withdrawal beyond what we are planning. There is another reason, which I already mentioned to you. It's not convenient to withdraw water during floods because there is a lot of turbidity. So during floods, usually the withdrawal is interrupted. Okay, very good. Now let's talk about the design of some side infrastructures, and in particular gravel trap and sand trap. Usually, when you make the preliminary design, usually when you design these interventions, these structures, you have to subdivide your design into phases, the preliminary design and the final design, or executive design, as we call it in Italian. And the reason is that usually you need a preliminary design in order to apply for the permission to withdraw water. Anytime that we withdraw water, we have to apply for a permission. Because, as I already mentioned to you, water is a public good, and anytime that we take it, we need a permission. And water is indeed a public good. You may remember that some 15 years ago, we had a referendum in Italy, which decided whether the water should be managed by private companies or not. And the referendum did not pass, which means that today the managers of water in Italy are a mix between private and public companies. But the referendum didn't decide about the public nature of water. This was never questioned. It was only meant to decide whether the management should be done by private companies. And therefore, let's keep in mind that water is a public good. And this is not questioned, and it's for almost all countries, the regulation is such that. Which means that you have to apply for a permission, and the permission is not easy to obtain, because then you have to make an assessment of the environmental impact, an assessment of the impact on the ecology of the river, and etc. There is a lot of documentation that is to be produced, and as I said, it's not easy to get the permission, which is in a way, I mean, on the one hand, it is a good thing that before intervening, before allowing interventions on rivers, rivers are a natural environment that is highly valuable. It's really delicate. It's a delicate environment that needs protection. So it's a good thing that we try to limit the interventions. On the other hand, you know that we need water, and in particular for producing energy. These small barrages are often built for producing hydropower, which is indeed a very good opportunity. It's in terms of sustainability, hydropower is highly sustainable. Of course, there are impacts. So no human intervention is free of impact on the environment. So on the one hand, it's a good thing that we try to limit these structures. On the other hand, we shouldn't exaggerate with the bureaucracy, because otherwise we undermine our efforts for reaching sustainability. If we want to decrease the CO2 emissions, I mean, hydropower is a very good solution. So in order to apply for the permission, you are required to make a preliminary design. It's not a very detailed design. You have just to estimate the design flow, to estimate the main behaviors of the spillway and their elevation. You have to make an assessment of the impact in terms of flood risk, but it's not a very detailed design. So for the preliminary design, and then once you are accepted, once that the permission, once that you got the permission, then you go with the final design, and the final design includes all the details. So in the preliminary design, we often make the design itself by using rules of thumb. And here I'm making this introduction because what I meant to say is that the gravel trap usually is designed in the preliminary design with a rule of thumb. We design the extension, the size of the sand trap, and usually we give as a rule of thumb that the gravel trap should have a length that is about half, a length and a volume that is about half the length and volume of the sand trap. Here it's not really half, as you see, they are comparable, but the rule of thumb is let's design the sand trap, and then once the sand trap is designed, the gravel trap is about half its extension. Now, so let me just now mention how the sand trap is designed. We don't go into the fine details because it is designed the sand trap by using the Stokes formula, which you already know, because there are other courses, I think, that are deriving it. And therefore, even if the Stokes formula, the derivation of the Stokes formula is included in my lectures here, in my tutorials, it's here. I don't ask this formula at the exam. So, but what I want to focus on now is the concept, not the formula, okay? So how is a sand trap design? Let me erase the blackboard. I have a question for you attending remotely, which I should already know the answer, but just be patient with me. If I don't share the screen, if I keep the screen shared, can you see the blackboard?
Yes, Professor.
Not Professor, it's not clear, and we have to zoom it and change the screen.
Okay, very good. Perfect.
Thank you.
Yeah. When I mute the participants, they still have the opportunity to unmute themselves. It's not killing them. Okay. Okay, so I keep the screen shared, and let me just to clarify the concept. So this is a longitudinal section of the sand trap. Okay, so there is a step dividing the sand trap from the gravel trap. This is the gravel trap. And this is the sand trap. Good. And then there is another step dividing the sand trap from the upstream tank. And then in the upstream tank, usually you have the pipe that is going downstream. Okay. The water level is something like this. Perfect. Now, first of all, some rules of thumb for the sand trap. The depth of the sand trap should be something like, let me call it H. H is about 50 centimeters. So it's not very deep for two reasons. First, if it is deep, it takes a long time to the particles, in suspended particles, to get to the bottom. If it's very shallow water, then its sedimentation is easier. Second, the sand trap, people may fall in, and so if it is very deep, then it may be dangerous. If it is very deep, sometimes we have the upstream tank that is very deep, and then you have to protect it to avoid that people accidentally fall in. So usually it's about 50 centimeters, and keep in mind that what is the flow that you have through the sand trap? The flow is the design flow, QP design flow. Good. And how to compute the velocity in the sand trap? Of course, I want the velocity to be reduced, because if I have a high velocity, then the sedimentation is problematic. It takes longer. Okay, so I want to keep the velocity reduced. I don't remember the order of magnitude. Let me see that I gave here. I think it is 0.05 meters per second. But let me just. I am pretty sure there is an order of magnitude here. Yeah. No. Yeah, 0.05, 0.15 meters per second. This is an order of magnitude for the velocity in the sand trap. What is an order of magnitude for the length of the sand trap? I saw sand traps that are 30 meters long. They are varying from 5 to maybe also 30 meters. You need a long time, a long residence time of water inside the sand trap. And what is the width of the sand trap? Something that I cannot see on the blackboard because it's perpendicular to the blackboard. On the blackboard, I see the longitudinal direction, but what is the width in the transversal direction? It may be 5 meters, 10 meters. This is the order of magnitude. Now, how can I compute the velocity? The velocity can be computed of water in the sand trap to make sure that I don't exceed the values 0.05, 0.15 meters per second. The velocity can be computed in this way. Let me just call it V. It's the design flow divided by, let me call the width W times H. So you divide the design flow by the transversal area. The design flow is expressed in length cube divided by time. If you divide the flow by the transversal area, which is the dimension is length square, you get as a result, in terms of dimension, length divided by time, which is a velocity. And therefore, if you divide, I repeat, the design flow by the transversal area of the sand trap, you get the velocity of the flow into the sand trap. Good. So what we do usually is to fix. We have the design flow to fix a tentative value for W and H and compute the velocity. And we see if the velocity, the order of magnitude, is fine. But then we have to make a check that particles have enough time to settle down inside the side trap. And what we do is to assume that there is a particle that is located at the entrance of the sand trap in correspondence of the water surface. And then we check if this particle has enough time, enough residence time to get to the bottom of the sand trap. What we know that the motion is parabolic because this particle has a velocity, which is the same velocity of water, but it is subjected to self-weight, to gravity. Gravity brings the particle down, and I have to check that the motion is something like this. So the center up should have a length enough, should be long enough in order to precisely allow the particle that is located on the water surface to reach the bottom. And in order to do that, in order to make this check, I need to know Ws, which is the velocity of sedimentation. Let me see if I use Ws as a symbol. Yes, Ws. And the Stokes formula gives the value of Ws depending on the kinematic viscosity of water, which is μ, depending on gamma s, which is the specific weight of the sediment, minus gamma, which is the specific weight of water, because these are immersed sediments, so their weight is lower. And then we multiply by the square of the diameter of the particle. This is the velocity of sedimentation, which is derived through the Stokes formula, which again, I don't ask you to prove. Okay. Now, I know h. If I divide h by the velocity Ws, what I obtain is d, which is the time required by the particle to settle down. Okay, now let me call the length of the center up L. L should be long enough in order to allow the particle to stay into the center up for the time t that is required the particle to settle down. So if I indicate the velocity in the center up with v, v times t, this is the length of the center up. Now, it may happen that, at the beginning, there is my arbitrary decision on the values of W and H. It may happen that it turns out that the velocity is too high, and then I have to change them. So I have to, typically, what I do is to increase W if I can, because if I can, because there might be no room. In the mountain rivers, usually on the sides, you don't have much room. So if I can, the easiest thing to do is to increase W, maybe by adopting two channels in the center up, like the scheme that I have shown to you before. Or in order to decrease the velocity, I can increase H. But if I increase H, then there is an increase of the time and then an increase of length. So at the end of the story, I look at the value of L. If L is something in the range 5 meters, 30 meters, if I have room, of course, I may be fine. If it is too long, then I may decide to play with W and H in some way, and it is an iterative process, okay? And the objective is to keep the velocity within the limits 0.05, 0.15. The objective is to keep the length contained, included into the range that I mentioned to you, 5 meters, 30 meters. And the objective is to make sure that your depth is not exceeding too much the value of 50 centimeters that I indicated to you. And then once that you estimated the length of the sand trap, the length of the gravel trap usually is about half, as I said. Okay. Good. Okay, let's move forward with the design of the head tank or upstream tank. So how it is designed? Here, the only requirement is to make sure, let me make another sketch of the blackboard, because I already made a sketch here, but it's too small. I want to make a zoom. So here I have the sand trap. And here I have the head tank or upstream tank. What is the purpose? As I said, the purpose is to make sure that the roof of the pipe is covered by enough water. So if I have the water level that is about here, if I have the water level that is about here, I have to make sure that I have a sufficient elevation over the roof of the pipe to avoid that I get air into it. Let me check what is the symbol that I used. No symbol. Okay, very good. Okay, so let me just make sure that I have a delta H here, which should be, let me indicate with V again, the velocity in the pipe, should be at least 1.5 V squared divided by 2G. Yeah. Okay, and so this is the only requirement that I impose. Keep in mind that usually here you have a grid to filter the floating material, to trap the floating material. Okay, now let me give some more details on the design of side structures. What do I mean with side structures? Let me just give you some more details on the main spillway, because I mentioned to you that it is advisable to adopt countermeasures to avoid erosion at the foot of the barrage. And to avoid erosion, what we usually do is for barrages that are not as important, we place boulders downstream to avoid erosion. But if the barrage is important, if the flow over the spillway is important, it's much better to use a solution like the one that you see on the screen, which means that the water flow is accompanied downstream by avoiding that the flow is detached by the structure downstream. Because if you adopt a vertical wall in the downstream side for the barrage, so you may decide to, if this is the riverbed, you may decide just to use a vertical wall as a river barrage, and then your flow takes this shape. Okay, so basically the flow is detached by the structure downstream. This is a situation that may be problematic if you have a huge flow. If you have a huge body of water that is flowing downstream. Why? May be problematic because then here you have turbulence and then you have downstream the water level, because there is the risk that void is created here, because the flow basically is has some cohesion with the air and brings the air out, and therefore here, as I said, the void may be created, which means that for the atmospheric pressure over the flow, you may have suddenly the flow collapsing against the structure. And then when it collapses against the structure, then air gets again into this space, into this volume, and the process starts again. And therefore you have a repeated collapse of the flow over the structure, which may be concerning. So for this reason, people had the idea of avoiding that there is an empty space, initially with air, but then with the void, between the flow and the structure. So the idea is that you do something like this. If this is the barrage, downstream, in a way, you shape the structure by following what is the ideal profile of the vein of water. So, in this way, basically your flow is lying over the structure with no empty space here, no empty volume. And the question, of course, is what is the shape? What is the ideal shape that I have to give to the downstream side of the barrage? And people did a lot of experimental activities in order to determine what is the best shape. And now we call this profile Krieger-Shimemi profile, because there were two persons, one Italian and one French, that independently made experiments, and they came to similar conclusions. Of course, the shape depends on the flow, on the amount of flow. The larger the flow, and the more extended downstream the profile should be. There is a link in my website that gives to you a document in French, which you don't have to open. I mean, it's just for your information, and gives to you the formula for the profile. Here they are. These are the two profiles, Shimemi and Krieger, and they are very similar. There are a couple of coefficients that are a little bit different, but they are very similar. And as I said, you don't have to learn them by memory. I just wanted to give you a link to a free document where you could find, in case you need it, you could find a reference for this profile. Okay. Now, second problem with the structure, if you have water pressure upstream and you have it, you have to avoid piping. What is piping? Piping is infiltration of water beneath, under the structure. So you may have water infiltrating upstream, passing the structure, passing by the structure in the underground and emerging downstream. This is extremely dangerous because when you have a water flow in a loose soil under a structure, then this flow tends to increase until the structure is flown downstream. And the reason is that, you know, water passing by tends to increase the width of the pores, the width of the microchannels that the water finds in the soil, and therefore these microchannels get increased, the flow increases, the energy increases, and then you have the flow of water that is increasing and increasing. It is the same problem for levees. You know that when there is a flood and you have a situation where you have a levee with significant amount of water depth on the river side, and of course on the land side you don't have any compensation because you don't have water, hopefully, and therefore people surveil the levees, because as soon as they see some water emerging at the land side foot of the levee, they put sandbags and they stop the flow, because otherwise the levee is rapidly blown out. And the same thing applies for river barrages. We have to avoid this risk, and there are empirical rules to determine whether there is indeed this risk, and there are more sophisticated computational solutions. I want to mention an empirical rule which I ask you to learn by memory, which is based on the computation of the horizontal and vertical component of the water flow under the structure. So if you see this sketch on the screen, you see with LV 1, 2, 3, and 4, the vertical component of the water path, under the assumption that if you have cutoffs, like in this case, what are cutoffs? They are the vertical teeth that you see upstream and downstream, which keep the structure anchored at the soil. These vertical walls, I call them vertical teeth, are called cutoffs, and they have the purpose of fixing the structure to the soil, but also to increase the length of the water path beneath, under the structure. And we assume that the path of water under the structure is the vertical path is given by the sum of all the vertical components, and therefore LV1 plus LV2. We don't assume that water remains in the deep soil. Water has the tendency of emerging again, and therefore water here, in this case, would go upstream, would go upward. So we have to sum LV1, LV2, LV3, and LV4. This is the vertical path, and then there is an horizontal path, which is given by LH1 plus LH2 plus LH3. Of course, the longer this path, and the better. So this is why the cutoffs are sometimes pushed very deep, like 20 meters. Sometimes it happens because we have also the technology for realizing very deep cutoffs. And what is the rule of thumb that we may follow? First of all, you have a water depth upstream, which is the driver of the piping. I think it is called here H. Let me see. And this is the rule. You divide H by the sum of the vertical path plus 1/3 of the horizontal path, because the vertical path is more effective. You divide H by the sum of vertical path plus 1/3 of the horizontal path, and then you get a number, and to be compared with a safety factor, which depends on the type of soil, which is given by tables. It's given by the literature. And therefore, you have to make sure that the value of F that is given by the literature is higher than the ratio between the water depth and the paths computed in this way. Okay. So if the requirement is not satisfied, what you have to do is to increase the depth of the cutoffs. Here there is a list of the techniques that can be used to create cutoffs. They can be created by backfilling a trench or shaft excavated under a bentonite slurry or similar supporting medium. So basically we excavate the soil and we fill the hole with bentonite. Bentonite is a fluid with a high specific weight, so it is pushed into the excavation in order to avoid that the soil is destabilized while excavating, and then we backfill the trench with material with limited permeability. Or the cutoff can be created by using sheet piles, and like these. You see in this figure, the sheet piles usually are made by iron, by metal, and they are just put into the soil, and these are very much used for levees and also for constructing arbors. Okay, I think that that's it. Just give me 1 second, I check if I said everything, but I think so. So again, what is the purpose of this discussion, which lasted about a couple of hours or some more than a couple of hours, is to give you an example of a technical design, an example of how structure, which is particularly used in the context of water resources management, can be designed with the focus on the hydraulic part of it. This is basically the only example that I will make of technical design in this course. So this is not a course that is focusing on technical design, it's more focusing on sustainability and let me say strategies for water resources management. Okay, do you have any question on this? Very good. Okay, now our next link would be climate change and water resources, but I want to postpone this later on. I prefer to postpone because it's very descriptive. It's a topic that is very recommendable, appropriate for in the final weeks of the course. So let's postpone it to maybe May. And instead, what I would like to discuss now with you is the assessment of human impact. We don't have much time now, we have about 20 minutes, but I think we can start. Okay, now, this is a Wikipedia page which is dedicated to the human impact on the environment. The human impact is, when we talk about sustainability, is a big question mark. And it's a challenge because on the one hand, it's unavoidable, and it's not only unavoidable, it's recommended. I mean, the natural environment is hostile. It's not easy to live in a pristine environment. So since the prehistory, humans made an effort to make interventions on the natural environment in order to minimize the risks and improve their well-being, their wealth, living conditions. And this implies that there is a mediation between the behavior of the natural environment and the needs of humans. If you think of an environment that is fully natural, and there are still a lot of natural environments in pristine conditions over the earth, it is something that we don't really get because we live in cities, we live in urbanized areas, and so we don't realize that outside the places where we are used to live, sometimes at a small distance, there are still pristine environments. And so if you make an experience of trying to live in a pristine environment, you understand that it's not easy. I give you an example of what I'm saying. There is a wood just uphill here, and from the faculty to the hills of Bologna. This wood was bought by the government in 1920 because they had to build the faculty. And they had to buy not only the area of the faculty, but also the wood which is uphill here. I don't know if they were obliged, because, you know, sometimes when you buy a field, you have to buy the whole piece of what's owned by a third person, and you can't fractionate it. Or maybe that they made it on purpose because they wanted to preserve the wood and the forest that was above the faculty. But the result was that this wood was closed, so it's impossible to get in because it's closed by gates. It was closed in 1930, and now it's almost 100 years that nobody goes in. And of course, there have been some people that went inside the wood for making some observations or just for checking. And what they reported is that the wood is back to pristine conditions, because if you take even a small piece of land and you avoid any human impact on it, any entrance of humans, very quickly it goes back to pristine conditions. Even a road, an highway, if you stop the traffic, then after a couple of years you see the grass that is flourishing on the pavement of the highway. So people reported that the wood is almost back to pristine conditions, and they recommended that it's kept closed because it's extremely dangerous. There are trees that are in an equilibrium that is highly unstable, and there is the risk that branches of trees fall down over people. So this is just to give an example. You just have to look at there, and you see this wood, and also. And it's very close by, and it's an example and it's very extended. So it's an example of an environment in pristine condition that is very close to us. We don't notice it, and it's at the same time it's dangerous to get in. But there are several other examples. But anyway, it's also true that humans have an impact, which is very considerable. There is also, if you think of the impact on climate is affecting also the areas that are still in pristine conditions, even if, the consequences of climate change on nature are in a way less concerning than the consequences of climate change on humans. Nature can adapt. The humans have a capability to adapt that is more limited. But anyway, it is true that there are impacts that are globally extended. On the other hand, it is also true that there are some consequences of human impact which are extremely relevant in the places where people live. So we know many examples: contamination of water, contamination of lakes, rivers, oceans, And contamination, of course, happens close by the human settlements, and therefore the evaluation of the human impact on the environment is extremely challenging and important, even if there are some places where the human impact is very reduced. The moral of the story is that where we live, we have an impact which is in some cases very relevant. When we focus on water resources, there is indeed an effect because the human impact implies water demands, implies pollution of water resources, and also implies the human evolution implies an increase of water demands. So the evaluation of this impact and the capability of taking impact into account in engineering design is a topical issue. But it's also a challenging question because we have very limited guidelines, very limited technical guidelines to estimate the human impact. So for instance, to give you some very simple example, we know that groundwater exploitation is a concern today in many areas of the world, but we still don't have the capability of estimating what is the volume of water available in the underground. So we still don't have the capability to understand if groundwater exploitation is sustainable. This is one example. A second relevant example is climate change. Climate change has many unknowns. Temperature dynamics is quite known. So we know that we are in a global warming period now. And the effect of climate change on temperatures, as I said, is well understood. But the effect of climate change on rainfall and therefore on river flow, water resources availability is for many reasons not completely known. So we still don't know if climate change is causing an increase, a global increase of flood risk. Of course, in some situations when floods are dominated by snow melt, of course climate change, global warming is increasing the risk of flood. But in other situations, like for instance for rivers like the Po River, which are driven, the floods in the Po River are driven by long-term precipitation that lasts for 1 week. We still don't know if these long-term precipitation events are affected by climate change. We fairly know that probably thunderstorms are affected, that the frequency of thunderstorms is increased, but for the long-term rainfall, we still have some question marks that are open. And therefore, if you have question marks on the forcing, you have a corresponding question mark amplified in the design. Because how can we take into account climate change in engineering design? This is really an open question, which is a question for engineers. It's a question for you, because the climatologist may tell you that there is a chance of something happening from now to 2050. But then it's a question for you how to incorporate these suggestions, these projections of climate into your design. These are called projections of climate, not predictions, to make clear that what we predict for climate change, it's not a quantitative prediction, it's a projection, they call it. And you may ask, what is the difference? If you reflect on the term, projections means an idea, okay, a projected idea of what may happen, but it's not a quantitative estimation. And we engineer, we need instead quantitative design variables, quantitative estimations. So indeed, the assessment of human impact, which is necessary in order to support technical design, is a challenge. And with this lecture, I'm trying to give you an overview and to elaborate with you some ideas. This lecture is something that you don't find into the books, so feel free to criticize it. It's a way to stimulate the discussion. There are several pictures that you may find on the web on the various effects of human impact. Indeed, in urbanized areas where we live, the human impact is multifaceted. So you see evaporation is influenced, and also the construction of dams means that you are increasing evaporation, and then you are deprivating the downstream rivers of part of the flow, and then there is the release of pollutants from cities, etc. And there is irrigation. A relevant human impact is given by food production. So it is an impact that is highly motivated. Sometimes we think of the human impact as something that is avoidable, like making some sacrifice or consuming less water, but actually, sometimes, the great majority of the human water use at the global level is for irrigation, and it's food production, which is something that we have to stimulate. And therefore, the question is a little bit complicated. And I want to discuss this with you with a positive view, because a negative view doesn't help. A negative view that assumes that humans are only negatively impacting the environment doesn't help much, because actually it's not like that. Sometimes humans are able to protect the environment and to restore the environment, so we shouldn't be too negative. On the other hand, we have to be proactive. Okay. First, human population is increasing, and this is potentially not a problem. I think that we have the resources for allowing the global population to reach values that are much higher than the current ones. On the other hand, it's clear that this is one of the reasons why the human impact is increasing. And it's not only a matter of global population. Keep in mind that also our demands for resources are increasing. And it's a demand that is justified. It's sometimes we also use more resources than we really need. But in terms of water, the fact that we have more demand of water now with respect to 100 years ago is justified, because now water, which is essential for the welfare, for the human well-being, it's available in the houses, and we take the shower more frequently. But these changes are the reason why the average life expectation for humans is increased, together with the progress in medicine, whatever. But it's also the fact that we have more access to water. It's one of the reasons why the life expectation is increased. And also, the availability of water is directly connected with our health, for obvious reasons. Okay, now, but how human impact can be estimated from a technical point of view? So how can I take into account climate change, whatever, from a technical point of view? Keep in mind that this is the technical aspect of it is usually not discussed in international forums where they mainly discuss about policy, about the efficient use of resources, but the technical implication in terms of quantitative evaluation of also of the outcome of policies is usually not discussed. It's a task for the engineers, and it is something that it is very often neglected. Okay, so I want to, together with you, to propose a framework for assessing human impact on water resources, which may be carried out by following these 4 steps. I go through the list and then we stop here for now. So, first of all, I believe that the first step must be a perceptual assessment of the effect of human impact and their priority. And I stress the emphasis on priority. So first of all, we have with critical analysis, that is a skill of the engineer. The capability to make a critical analysis must be our skill. We should really assess the effect of human impact and the priority. And why I stress this? Because when we follow the media or sometimes also policymakers, it is clear if you have the capability of making a critical analysis, it is clear that sometimes they make a wrong estimation of priorities. Sometimes they overestimate a kind of impact, underestimate other impacts. For instance, I give you an example. One thing that I really don't understand is why today we are still underestimating the likelihood of long-term droughts. It's a risk that we don't consider. Long-term droughts has always been a risk. From the Bible reports of 7 years of abundance and 7 years of famine, which was precisely due to the fact that also in the ancient times, sometimes it happened that it didn't rain for several years. And also, if you look at the historical data that in Italy we have of rainfall, you see that there are long-term droughts that are occurring. And this is a risk that in the past was a challenge. Today would be a disaster, because with the current needs for water, if in our region, if in Bologna, we get 5 years of minus 30% of precipitation, it's a disaster. Because we are consuming much more water than in the past. Water is essential also for commercial activities, for cooling several industries, several engines, and it is the consequence of a long-term drought would be extremely more impacting with respect to 100 years ago. And in fact, we had recently several examples at the global level of droughts that generated a huge impact. In Australia, from 2001 to 2010, there was a drought that lasted 10 years. And they built desalination plants because they thought that it was the only way. They thought that the drought was going to last forever. And they built a lot of desalination plants as an alternative. But then after in 2011, the drought ceased. In California, from 2013 to 2017, they had 5 years of drought, and then it ceased. In South Africa, from 2014 to 2018, same thing. So, I mean, this thing happened, and I still don't understand why it is not considered a matter of concern. This is, I think, something that it's not strictly related to human impact. Is a risk for humans that is still underestimated by policymakers, or another risk that is frequently underestimated is the risk of earthquakes, or the risk of volcanic eruption, even better example than earthquakes. Can you understand why we have plenty of volcanoes in Italy? Why we are basically ignoring the probability that some of our volcanoes make an eruption like they did in the past. And also another risk that is underestimated, we are discovering in the Mediterranean Sea a lot of submarine volcanoes, which represent a relevant risk of tsunami. And some of them were discovered only recently. And I mean, these risks are basically ignored, while there is a lot of attention on other risks that, in my opinion, have lower priority. So I think that the first step must be this perceptual assessment and priority. So what is priority? It's groundwater with respect to surface water. Human impact on groundwater is priority with respect to surface water or not. It depends on the context. But we have to try to be very objective and to identify what are the facts we have to be concerned about. Second step is the identification of objective and robust methods for assessing each impact. So, okay, it's groundwater exploitation, the priority, perfect. How can we use our current knowledge in order to improve our knowledge of groundwater systems? Development of future scenarios, because this is the role of the engineer. The engineer has to make prediction. Design variables, when you estimate a design variable, you're making a prediction of what may happen into the future. And then, and I stress this, uncertainty assessment. An engineer has the need of knowing uncertainty in a reliable way, which is not so easy. It's not so easy because sometimes we have predictions, but not uncertainty of the predictions. And if the engineer, if it doesn't have uncertainty, cannot work. And again, uncertainty assessment in a proper way, not just a guess. It should be a quantitative assessment of uncertainty. Okay, I think we can stop here and then I will move forward with additional considerations on Monday. We don't have lectures on Thursday next week, of course. Questions? Okay, thanks a lot.
Thank you, Professor. Have a good day.
Yeah, you too.